This is the 3.3.1 review on chemical reactions. So this unit was all about chemical reactions, how chemicals change through the unbonding and new bonding of the elements that make up the chemicals, okay? So reactions involve changes in energy. Okay, so some reactions when they run release energy and some absorb heat energy. So in this particular section, you're going to be looking at chemical reactions and how we can sort of read them. You first looked at the following objectives: explain and model the law of conservation of mass, apply the mole concept to calculate quantities or amounts in chemical reactions, describe different types of chemical reactions, and then explain the outcome of simple chemical reactions. In other words, predict what the outcome would be, knowing what you're starting with. Balancing chemical equations. So you probably already have had some experience with balancing chemical equations from middle school. So I'm just going to go through this super quick. Basically, what you want to look at is the red number in front. That's called the coefficient. And that helps you balance the number of atoms on the reactant side compared to the product side. So you'll notice that you have a sodium and chlorine gas, which comes as a pair, written as Cl2, reacts to give you sodium chloride, NaCl. So in order to balance this, you have to have two chlorines that are on the left also have to be on the right. But we can't just stick a little subscript 2 after the chlorine because that changes the chemical makeup, okay? That's not how we balance equations. The only way that we can balance the equation is to put a coefficient of 2 in front. And so when you do that, that 2 not only applies to the chlorine, but it also applies to the sodium. So to address the two sodiums on the right, you're going to put a 2 in front of the sodium on the left, and now you have a balanced equation. Moles, the mole idea is just this idea that atoms have different masses. The unit of the mole is used to keep track of the amount of atoms, okay? So 1 mole is a really large number, and it has to be large because you're talking about really small atoms, okay? So the magical thing is that the mass that you see on the periodic table is for a mole of the substance, okay? So we call that the molar mass. So if you look on the periodic table at sodium, you will see that its mass is 22.99 grams per mole. That's what we call the molar mass, okay? We multiply that by 2 because in balancing the equation, we said there has to be 2 sodiums, so you get a total of 45.98. The chlorine has a mass of 35.45. We multiply that by 2 because they're 2 bonded together. We call this diatomic, and you get 70.9 for 1 mole of chlorine gas. And then the products, if you add them up, you will see that you get 116.88. So this table kind of shows you how to balance equations and show that your equation is balanced by showing that the masses on the left side are equal to the masses on the right. The different types of reactions you looked at, the first one is called the synthesis reaction. Synthesis means building or putting together. And so in a synthesis reaction, you have 2 separate species, substances, elements or compounds, that combine to form 1 species. Okay, so in this case, a single sodium with chlorine combines to form 1 molecule of sodium chloride. Okay, so this is an example of a synthesis reaction between a metal and a nonmetal. The sodium being the metal, the chlorine being the nonmetal. Another example is a synthesis reaction between 2 nonmetals. So here carbon and oxygen, again another diatomic molecule, combine to form carbon dioxide. Okay, 2 things combine to form 1 thing. That's called a synthesis reaction. okay? This is held together by covalent bonds, whereas the metal and nonmetal are held together by ionic bonds, okay? You will also notice that there are no coefficients here because the way that the equation is originally written, it's already balanced. So we don't use any coefficients to balance it. The next kind of reaction is a decomposition reaction. Okay, decomposition is literally the opposite of a synthesis reaction. It's the reverse, where you take one thing and in the reaction you break it up into its component parts. So here we have water breaking up into hydrogen and oxygen. This process is called hydrolysis. And to make it happen, you actually have to run electricity through the water to get the oxygen and the hydrogen to separate. Single replacement reactions. This is basically where you have one element in a compound and the metals switch places. Okay, so you'll see you start with Fe and copper sulfate and you switch to copper and iron sulfate. Okay, so the Fe and the copper switched places. The iron started out as a solid neutral atom and ended up as an ion in solution, and the copper started out as an ion and ended up as an atom, a neutral solid metal, and you can see the copper right here on the nail. Okay, so that's a single replacement reaction. To understand whether a single replacement reaction will happen or will not happen, you have to look at something called the activity series. Okay, so the activity series is a list of the metals from most active at the top to least active at the bottom. So if the metal that's by itself is more active than the metal that's in compound, then it will take its place. If it's not, then it will not take its place. So for example, in the example that we were just looking at, iron is by itself. So we want to see if iron is more active than copper. Can it take copper's place? So if we look, iron is more active than copper, so it will take copper's place. Okay, the reverse is not true. Copper is not more active than iron. So the reverse of this reaction will not happen. The reaction will never go this way. Okay, all right. Double replacement reactions are when you have two compounds and they switch partners. And when they switch partners, sometimes one of the molecules that is formed is not soluble in water. And so what you get is what's called a precipitate. Okay, let's watch this video.
Forming a precipitate. Lead-2 nitrate and sodium iodide are both soluble. They dissolve in water to make colorless solutions. In each solution, the negative and positive ions are separated from one another and surrounded by water. When the solutions are mixed together, an insoluble yellow solid forms. This precipitate is lead iodide. It forms because the lead ions and iodide ions are attracted to each other in the solution and form an insoluble solid. The other ions form sodium nitrate, which is soluble in water. So those ions stay in solution. The precipitate is the product of the double replacement reaction between lead-2 nitrate and sodium iodide. In this reaction, the lead and the sodium switch places. One product, the lead iodide, is the solid precipitate. The other, sodium nitrate, stays dissolved in the solution.
So, a little fun fact.
Which is soluble in water.
This bright yellow is what they used to make paint. They used to make paint out of lead. And the lead compounds can make really bright colors, bright red and bright yellow. And so they would paint kids' rooms with these lead-based paints. And kids, not knowing any better, would put paint chips in their mouth and get lead poisoning. And lead poisoning leads to the inability to think well, cognitive slowness, and things like that. So they have since stopped making paint out of lead. Okay, Oxidation reduction reactions, also called redox reactions. This is where electrons are transferred between atoms. Okay, so oxidation reduction reactions can happen during synthesis, like for example here. Iron and oxygen can combine to form iron oxide. This is a redox reaction because electrons are exchanged. And you can see electrons are exchanged here. Iron goes from being a 0 charge to a +3 charge. It loses 3 electrons. Oxygen goes from being O2 to O-2. So it gains 4 electrons. Okay. Obviously, these are not balanced. Otherwise, the number of electrons you lost and the number of electrons you gained would have to be equal. But just know the idea of oxidation reduction is an exchange of electrons between the atoms. Okay. Decomposition reactions can also be redox reactions. Here, the oxygen once again gives up 4 electrons, and in this case, hydrogen gains electrons. So this is also a redox reaction. Single replacement reactions can be redox reactions. This is the example we saw earlier. If we look closely at each of the metals, you'll notice that iron loses 2 electrons in the process, and copper ion gains 2 electrons to become a solid copper that you can see on the nail. Okay. The double replacement reactions are not redox reactions. They are not redox reactions because they don't exchange electrons, okay? The charges of all of these ions stays the same throughout the whole process. So electrons are not exchanged, so this is not a redox reaction. Okay. So that's a summary of the types of reactions. Here's one more, combustion reactions. Combustion reactions always react with O2, okay? This is magnesium reacting with O2. It actually has a very, very bright flame. This is like if you have a gas stove, you burn methane. This is methane in the presence of oxygen, gives you carbon dioxide and water. What's really important about combustion reactions is that combustion reactions release a large amount of heat and light energy, okay? We can heat up lots of things with combustion reactions. Okay, so this is part 2 of your review for Unit 3, and this is factors affecting chemical reactions. Factors affecting chemical reactions. Here are the objectives. You should be able to classify energy changes as endo or exothermic. You should be able to explain how releasing or absorbing energy can change the total bond energy. Develop a model to illustrate the release or absorption of energy from a chemical reaction. And explain factors like concentration, temperature, and catalyst, how that affects the rate of chemical reaction. Explain dynamic equilibrium. And refine the design of a chemical system to produce increased amounts of equilibrium, at equilibrium. So that's Le Chatelier's principle that they're referring to there. Okay, absorbing and releasing energy. This
energy changes during a chemical reaction. Every system of molecules contains chemical energy. You can think of this as the potential energy of the system, but you have to add energy to the system in order to start a chemical reaction.
You'll notice that the molecules in the box started moving faster because he added energy.
When the molecules of the reactants have enough energy, they'll collide with one another with enough force to break their bonds. The graph shows energy being absorbed by the system of hydrogen and oxygen molecules.
Notice the y-axis is potential energy of the system, okay? So this is gaining energy from you heating it.
In other words, the potential energy of the reactants is increasing. The system has the maximum amount of potential energy as its reactants' bonds are breaking, but it will not stay in this state for very long. The molecules are very unstable and reactive in this high energy state. To become more stable, new bonds form as bonds are breaking. A stable molecule has less potential energy than an unstable molecule.
That's a really important statement. A stable molecule has less potential energy than an unstable molecule.
So, as the molecules collide, bonds form between hydrogen and oxygen atoms to make water molecules, and energy is released into the surroundings. The potential energy of the system decreases.
You'll also notice that the potential energy went below the starting potential energy. So the question is then, what happens to this extra energy? Where does it go? Well, it gets released into the environment as heat. Okay, so your container would feel hotter than what you started with. Okay, so exothermic reactions are what we're talking about. Combustion of propane and rusting are both exothermic reaction. Remember, exo means exit. Heat is exiting the system because the substances that have formed as a product are much more stable. And if they're stable, they need less potential energy. So the extra energy is released as heat. Exothermic reactions. The opposite is endothermic reactions. This is where energy is absorbed, like in an instant cold pack or in cooking. Energy has to be provided and the chemicals have to absorb that energy to form the product because the product is less stable than the reactants. So in order for the products to form, you have to give it extra energy. It has to absorb that energy. So why does this get cold? Because it absorbs the energy, the heat energy from its surroundings. And so the surroundings will feel colder. Remember, when it absorbs the energy, it doesn't keep it as heat energy. It converts it into a chemical bond energy that does not feel like heat. So that's why that gets cold. Okay, activation energy. This is the energy you need to break bonds. Okay, so your reactants start here. There's a certain amount of energy that needs to be gained in order for the bonds of the reactants to break. That is called activation energy. Once that energy has been reached, bonds will break, new bonds will form, and if the new bonds that form are more stable, then the potential energy will drop and energy will be released. All right, how do concentration and reaction rate affect the how fast or the rate of chemical reactions? So I'll have you watch this video on your own. I'm not going to play it right now just to save time, but the idea here is the more molecules of the reactant you have, the more likely there is that there will be collisions between those molecules, which will then produce a product. So higher concentration means you will produce products faster because there's a higher chance of collisions. So increase the concentration, increase the reaction rate. That's the take-home message. Temperature, it's the same idea. If you increase the temperature of the reactants, the molecules are going to move around faster. And if the molecules are moving around faster, there's a higher chance that they're going to collide. And when they collide, there's a higher chance that they will form new bonds. Okay? Temperature, increase the temperature, you increase the reaction rate. Again, I encourage you to watch the videos. Okay, a catalyst is a chemical that you add to a chemical reaction, a separate chemical you add, and all it does is it provides an alternate reaction path that lowers the activation energy. Okay, so this is without a catalyst, this is with a catalyst. It lowers the activation energy. And then finally, the idea of dynamic equilibrium. Some reactions are reversible, okay? Instead of going all the way to completion, they reach a state where the forward and backward reactions are still happening, but they're happening at the same rate. As a result, the concentration of the products and reactants stay the same. It's kind of like, again, watch the video on your own. It's kind of like having a capacity of 15 people in a room. So if 2 people leave, 2 people have to come in, or 2 people are allowed to come in. If 10 people leave, 10 more people are allowed to come in. It's kind of like standing at line in Trader Joe's these days, right? You can't get in until someone leaves because they have to have the same number of people inside. That's dynamic equilibrium. Now you can shift this equilibrium in several different ways. This is called Le Chatelier's principle. Okay, in a chemical reaction, the forward and backward reaction rates are equal. But if the products or reactants are added to or removed from the system, the rate of the forward and backward reaction increases until a new equilibrium is reached. Okay, so it's essentially if you add a bunch of stuff to something that's already at equilibrium, you're what we call stressing the equilibrium. And so the reaction will either shift towards the reactants or shift towards the products to use up the extra stuff you added. Okay? Excuse me. All right. Lastly, this simulation looks at gas equilibrium and pressure. So essentially, you count the number of gas molecules by counting the number of moles. Excuse me. So I have 1 mole of nitrogen and 3 moles of hydrogen as my reactants. That's a total of 4. And I have only 2 moles of ammonia as my product. So I have more moles of gas on the left than I do on the right. That means that if I put more pressure on this, this is going to shift to where there's less moles of gas. In this case, ammonia, the red molecules. If I decrease the pressure, it's going to shift to make more gas molecules. In this case, nitrogen and hydrogen are the blue and gray molecules. So this is kind of like what Le Chatelier's principle is about, shifting equilibrium by stressing the reaction. Okay, again, play with this so that you have a better understanding of what is going on here. If you have questions, shoot me an email. I'm happy to jump on Zoom and help you out. Have a great day.